long question ahead, and it'll test our intuition and our understanding of what these rules actually are. So let's dive in. The statement here, a stationary magnetic dipole M equals mz hat is situated above an infinite uniform surface current K equal mx hat. A. Find the torque on the dipole using the equation 6.1. B. Suppose that the surface current consists of a uniform surface charge sigma moving at velocity v equal vx hat so that k equal sigma v, and the magnetic dipole consists of a uniform line charge lambda circulating at speed v, the same v, around a square loop of side length L as shown, so that m is equal to lambda VL squared. Examine the same configuration from the point of view of system S bar moving in the x direction at speed v. In S bar, the surface charge is at rest, so this generates no magnetic field. Show that in the same frame, the current loop carries an electric dipole moment, and calculate the resulting torque using equation 4.4. Holy cow, a lot of words going on right there, but this is what the relativistic regime allows us to do. It interchanges the electric and magnetic phenomena in the perspective of the reference frame we're using. Let's go. Here's our diagram where we're seeing that we have surface current density K moving to the right with V, and it has a charge density of sigma. But here goes that loop that we have with the magnetic moment or magnetic dipole moment pointing up. We'll reference this again maybe a couple times, but come back to it as much as you need to. Let's get into the work. All right, so part A, what we know is that the magnetic field for the surface current is B equal negative mu naught over 2 Ky hat. And the torque is due to the magnetic dipole, and the field is N equal M cross B, where we know what M is, and that's in the z hat direction, cross product with this field. So we see that the torque is equal to mu naught over 2 mk x hat. B, in the new frame, however, M is equal to lambda V squared, and K is equal to, we have sigma V, and then that's equal to V x hat. So we see that the torque here is equal to mu over 2, and then all of this stuff times all that stuff, same stuff we would have had in the cross product stuff. That being said, we have a whole lot of constants in this box. Mu naught over 2, lambda sigma V squared L squared x hat. Here's where the things start getting tricky, is that we have to go back to what actually got what was actually contracted in the moving frame based on the Lorenz's transformation rules. So charge density on the front side, lambda naught, is equal to gives us lambda equal gamma lambda naught. Density on the backside, bar, is equal to lambda bar equal gamma bar lambda naught, where V bar is equal to the Einstein velocity rule, 2V over 1 plus V squared over C squared. Okay, you see where these things are starting to come into account, and why we need to pay very close attention to the velocity addition rules and the contraction length rules. Okay. As you see here, V bar, when we're running around the backside, that's going to be counter versus when because we have the frame moving one way, the velocity moving the other way, so that's going to add to 0. Frame moving this way, then they're going to join together, things of that nature. Of course, in the direction perpendicular, we don't have to worry. It's only in the direction that we're moving that we have the contraction. Let's tidy this up now. Gamma bar, of course, is equal to 1 over the square root of 1 minus V bar squared over C squared, but we just had to solve for what V bar was, and squaring that gives us the 2V, all that thing squared. Holy moly, take a second to look at all this nasty algebra. We're trying to factor out a 1 over 1 plus V squared over C squared. We'll send that to the numerator here. If we distribute and FOIL out this thing, then we see that we get a factor that cancels with this. we could recombine, refoil down, or refactor down, put it as a square, get rid of it, and then we see we have a familiar plus over minus relationship. And of course, we see that this in the bottom is a gamma squared. So we have a gamma squared times 1 plus v squared over c squared. Holy moly, holy moly, holy moly. That is gross, gross, gross. Be careful, be careful, be careful. Alright, so the length of the front and back sides of the frame have to have the contraction, so that's L over gamma. So net charge on the side is Q plus is equal to lambda bar over lambda bar times L over gamma, and then we'll let the color coordination start speaking for itself. We just saw what gamma bar was right up here, plug it in. We have lambda naught, which is equal to lambda over gamma. Then we also have L over gamma, so we have a couple gammas here canceling, and we see what we're left with in that frame. Note the charge on the front side is Q minus, and we have a similar situation here, except now we have 1 over gamma squared lambda L. So because the velocity in a shifting frame made the front and back sides, which are running parallel to the motion, do opposite things, because one contracts, increases, the other contracts based on gamma and the relative velocities based on Einstein's rules. That's going to change the charge distribution and all the other stuff, and that's what creates the dipole thing that we're going to have. So the dipole moment, note charges on the sides are equal, so what we have here creates this thing. And that's the dipole moment of the electric dipole because of the contraction factors. That being said, what a wonderful little thing we have here. And let's clean everything up that we can, plug everything in that we know, and tidy up algebraically. We see that the dipole moment P results in a lambda L squared V squared over C squared in the y-hat direction, of course. And so, of course, if that's the case, anything like this with a parallel plate, or a plate like this is going to have a field of sigma naught over 2 epsilon naught z hat, pointing up, of course, if it's positive, where sigma is equal to gamma sigma naught, so N is equal to P cross E. And we see that after some clever substitutions here with the gammas, and we see that we get C squared, epsilon naught squared, all that stuff, we get 1 over gamma mu naught, because we're getting rid of the C squared and epsilon naught, over 2 lambda sigma L squared V squared x hat, and we see that we have a lambda, and so we have the sigma and the lambda here. So apart from the relativistic factor of gamma, the torque is the same in both systems, but S is the torque exerted by a magnetic field from a magnetic dipole, whereas S bar, it is a torque exerted by an electric field on the electric dipole. How freaking cool! This is fascinating. No wonder Einstein couldn't stop thinking about the need for a connecting between these two phenomena outside of just it is what it is. That is amazing.